Hi everybody, welcome to this video about making estimates using finite sums. This is our fifth video in our series on integration. We can estimate and approximate answers to a number of problems by using finite sums. In this video, we'll learn about finite sums. We're going to learn what they are, and we'll see how we can use them to find the area underneath the curve on a graph. In the next videos, we'll see how definite integrals are the limit of a particular type of sum, referred to as a Riemann sum. The area under a curve on a graph is often a useful and meaningful quantity. It can provide answers to a number of questions and problems, depending upon what the curve represents. In some cases, the area under a curve can be calculated easily. In other cases, it can be more difficult to calculate. We'll now see some examples that show how finding the area under a curve can help us to solve problems. For our first example, we're looking at calculating distance traveled at a constant speed. We want to calculate the distance traveled by a car. The car travels at a constant speed of 10 meters per second, and it travels for 10 seconds. Now, we know that distance traveled is equal to speed multiplied by time. So the distance traveled by our car is equal to 10 meters per second, its speed, multiplied by the time, 10 seconds, which gives us 10 multiplied by 10, 100 meters. We can also solve this graphically. When we plot the speed of the car versus time, the distance traveled by the car is equal to the area under the curve. To explain this, we can look at the plot of speed versus time on the right hand side. So here on this graph, we've got a plot of speed in meters per second versus time in seconds. So on our x-axis, we've got our time of 10 seconds, and on our y-axis, we've got our speed of 10 meters per second. And the area underneath our curve is represented in the highlighted blue rectangle shape. Now, if we wanted to calculate the area of that shape, we'd multiply the height by the width. But in this case, the height corresponds to the speed, 10 meters per second, and the width corresponds to the time of 10 seconds. So when calculating the area and multiplying the height by the width, what we're actually doing is we're multiplying the speed of 10 meters per second by the time of 10 seconds. So the area of the shape under the curve, the area underneath the curve, that corresponds to our distance traveled by our car. Now we can calculate this area as the area of a rectangle with sides of 10 by 10. The area is equal to 10 by 10, which is equal to 100. For our units, we're multiplying 10 meters per second by 10 seconds. So the seconds cancel above and below the line, giving us units of meters. Now, this gives us an answer of 100 meters as before. In our second example now, we're going to expand on this idea. Here for our second example, we're calculating the distance traveled while accelerating. We want to calculate the distance traveled by a car again, but this time the car accelerates from rest, from a full stop. The speed of the car is equal to the time squared, and we want to calculate the distance traveled in 5 seconds. So from this information, our speed v as a function of t, time, that's equal to our time t squared, and time ranges from 0 to 5 seconds. Now we know that distance traveled is equal to speed multiplied by time, but this time our speed is not constant, so we cannot use this equation to solve the problem, because at our time of 0 our speed is equal to 0. At a time of 1 our speed is equal to 1 squared, which is equal to 1 meters per second. At a time of 2 seconds our speed is equal to 2 squared, which is equal to 4 meters per second. So we don't have any single value of speed that we can, we don't have any single constant value of speed that we can multiply by that 5-second value. So we can't simply use the distance traveled equals speed multiplied by time formula. But we can solve the problem graphically. If we can calculate the area under the curve as before, we will have found the distance traveled. So if we look at the right hand side of the screen here, we've got a plot of speed in meters per second versus time in seconds on this graph for the accelerating car. And we can see here that the car starts at rest and continuously accelerates for the 5 seconds, with its speed continuously increasing for those 5 seconds. So what we want to do here is we want to calculate the area underneath the curve, because if we can work out that area underneath the curve, that'll be equal to our distance traveled of our car. Now we don't have a straightforward formula like previously where we could multiply one side length by another to find the area, because the shape of our curve it's more complex now. It's not a simple rectangle shape. But we can approximate the area under the curve by using the sum of the area of a number of smaller rectangles. So that's what we're doing here on the plot on the right hand side. What we've done is we've divided up the time into 2 sections. We've got a first section of 2.5 seconds and a second section of 2.5 seconds. So that first rectangle is approximating, representing the area underneath the curve in the first 2.5 seconds, and that second larger rectangle, that's approximating, representing the area underneath the curve in that second 2.5 second section. So here we have 2 rectangles that are approximating the area under the curve. The height of a rectangle is the function value at the midpoint of the rectangle. So for that first rectangle there, its height corresponds to the speed at the midway point of the rectangle. So it's got a width of 2.5 seconds, so its midway point is 1.25 seconds. So its height corresponds to the speed at 1.25 seconds. And for the second rectangle, well, its midway point is at 3.75 seconds. So its height corresponds to the speed at 3.75 seconds. So what we want to do is we want to calculate the sum of the area of the rectangles. So for each rectangle, we want to multiply the height by the width, and then we want to add the area of each rectangle. So when we do that, it corresponds to 1.56, the height of the first rectangle, by 2.5, its width, plus 14.06, the height of the second rectangle, by 2.5, the second rectangle's width, which works out to be 3.9 plus 35.15, which gives us an answer of 39.05 units for the area of the two rectangles combined. Now, as before, our units are meters, so our answer is 39.05 meters. So our estimate of the distance traveled by the car by approximating the area under the curve with two rectangles is 39.05 meters. Now, we can imagine that if we used more rectangles with smaller widths, our estimate of the area, it'll get closer to the true area under the curve. Because when we look at that plot with the two rectangles, we can imagine that there may be some significant error involved in this approximation, that the area of a given rectangle, that it may not match up exactly with the area under the curve that it's approximating. But we could imagine that if we used more and more and more rectangles with smaller and smaller widths, that the combined shape of the rectangles, it would more and more closely align and agree with the true shape of the curve, and that then the combined area of the rectangles will get closer and closer to the true area under the curve. So we started to do that here on the plot on the right hand side. Now we're using a larger number of rectangles. In this case, we're using 5 rectangles with a width of 1 unit, 1 second each. So we want to calculate the sum of the area of these rectangles. We do this in the same way that we did before. This time we get 0.25, the height of the first rectangle, multiplied by 1 unit, its width, plus 2.25, the height of the second rectangle, multiplied by 1, its width, and so on for the other rectangles. And we add up those areas and we get an answer of 41.50 units. So now, using a large number of rectangles, 5 rectangles this time, our estimate of distance traveled is now 41.50 meters. So our estimate has changed by about 2.5 units. Now we can go further again. We can use even smaller rectangle widths and even more rectangles. So this time we're using 10 rectangles with a width of 0.5 units, 0.5 seconds each. And this is illustrated here on the graph on the right hand side. Now we're using 10 rectangles. And we can see that the combined shape of the rectangles that more closely approximates the shape of the curve. And when we calculate the sum of the areas of these rectangles in the same way that we've been doing before, now our estimate of the distance traveled, now it becomes 41.55 meters. So what we see is that as the number of rectangles increases and the rectangle width gets smaller and smaller, we get closer and closer to the true value of the area under the curve. And we can see this in this table of results here on the bottom left hand of your screen. When we used two rectangles, our rectangle width was 2.5 units, and the sum of our areas of our rectangles was 39.05 units. When we used 5 rectangles with a rectangle width of 1 unit each, the sum of the areas of our rectangles was 41.50 units. And when we increased up to 10 rectangles with a rectangle width of 0.5 units each, some of our areas became 41.55 units. So what we see is that as the number of rectangles increases and increases, and the rectangle width gets smaller and smaller and smaller, the sum of the areas, it converges on, and it gets closer and closer to a single true value of the area under the curve. To estimate very accurately using a finite sum, we want to use a rectangle width, which is referred to as an interval length, small enough that the function value is effectively constant within the interval. So in our example, our function value has been speed. So we want to use a rectangle width, an interval length that's small enough that the speed within that rectangle in this example is effectively constant. And a key point is that we're working with a sum of function values multiplied by interval lengths. The area under the curve is estimated with a sum of function values multiplied by interval lengths. And here we're using the function value at the center of each interval. So in our example, with rectangle widths, interval lengths of 0.5 units, our first function value will be taken at the center of that first 0.5. So it'll be 0.25. The second interval will be at the center of that second 0.5, so 0.75, and so on. So we can calculate out our area as our function value, f of x, where x is equal to 0.25, so f of 0.25 multiplied by our interval width 0.5, plus our function value for our second interval, our second rectangle width, which is f of x, where x is 0.75, so f of 0.75 multiplied by our interval length 0.5, and so on for each interval, for each rectangle width, all the way up to our last one, where f of x and x is corresponding to 4.75, so f of 4.75 multiplied by 0.5, our interval length, our rectangle width. And that's how we calculate the area under the curve with our finite sum. So our finite sum is a sum of function values multiplied by interval lengths. And in this video, we've used a finite sum to estimate the area under the curve. Now, we can use finite sums to solve a wide range of problems. We can use them to perform calculations with parameters that are varying continuously, as we've done here. So in our example number 2, we were working with a speed parameter that was varying continuously with time. And we couldn't use our straightforward distance traveled equals speed by time calculation, but by using a finite sum to calculate the area underneath the curve, we were still able to calculate the distance traveled. We can also use them to calculate the volumes of shapes, so we can use finite sums to calculate the volumes of shapes, and we can use them to do a lot more too. In our next videos, we're going to learn about definite integrals. And we'll learn that definite integrals are the limit of a particular type of sum, referred to as a Riemann sum. I hope that you've found this video useful. Thanks a lot for watching this video, and see you next video.